Okay, so now let's talk about confidence intervals and see why do we care about them. Okay, so let me actually quickly write down an example. Imagine we are regressing log wage on beta 0 plus beta 1 education plus u. I went ahead and calculated the number. So let's say the log wage, the estimated version, put a hat on top of it with some number. I don't know what it is. I'm not interested in this intercept. I really don't care what it is. But this number is accurate. So this is 0.085. Education. There's a dot here. So how do we interpret that? If education increased by 1 unit, the wage is going to increase, hourly wage is going to increase by 8.5%, right? Okay, now we know that this is our best guess for the population parameter, which is, let's say, beta 1, right? We are interested to make a story for the entire population. I hope that I can say in the entire population, education and wages are positively correlated, right? But the sad news is that this beta 1 is never observable, right? So we're going to say that if this is your beta 1, I know for a fact that it's not observable. I use one sample. In that one sample, the estimated version for beta 1, the beta hat 1 was 0.85. So maybe this is 0.85. If I use another sample, maybe it's 0.8. If I use another sample, maybe it's 0.7, right? You get the idea? So if I use different samples, not maybe, for a fact, I will get different numbers, okay? Because OLS is calculating a different number if you use different samples, right? Yes, the sad news is that beta 1 is not observable, but the good news is that I can come up with a range. I can say that, you know what? It's fine that I cannot, what's the color, blue? It's fine that I cannot observe this beta 1. However, I can construct a confidence interval around that. I can come up with a lower bound and an upper bound, and then make statements with probabilities. I can say, for example, with 95% probability, this unobserved beta 1 is going to be between two numbers. So again, I'm making up these numbers. 0.06, I think 6 is very small because education is significant. 0.07, 0.09. Okay, again, with 95% probability. This is a very good news, right? Because, okay, you could not give me one exact number, but you can tell me with what probabilities, in this case 95 probabilities, that unobserved relationship is going to be between 7% and 9%. So whatever your education is, whatever sample that you're looking at, if it is the entire population or different sample, with 95% probability, the smallest effect is 7%. The largest effect of education on wage is going to be 9%. So, and then if you like these numbers, you're going to go ahead and say that, okay, well, I have to spend some money for education because regardless of the sample that I'm dealing with, and let's say it was significant and etc., this education turns out to be an important variable, right? So this is what the confidence interval is going to do for us. So that's why it's very important. How can we construct it mathematically? It's going to be equal to what? It's going to be equal to beta hat j plus minus, this is our critical value for the significance level, whatever it is, multiply the standard deviation, standard error of the beta hat j, right? So for example, I don't know, let's say we work with this sample that we had, 0.8085. Let me fix it, 0.085, right? If I go ahead and calculate a critical value for 95% significance level, so I call it C05. Let's say this number is roughly 1.96. And then, because by construction it's two-tailed, let's say that's the case. And then if I multiply this number by the standard error, so if I go 1.96 standard deviation above, I'll get to this point. If I get 1.96 standard deviation below, I get this point, right? So lower bound and upper bound. So this is how we calculate the lower bound and upper bound for confidence interval. And we say that our variable that you're interested, the coefficient here, beta 1, is between these two numbers, lower bound, upper bound. With what? With what probability? 95% problem. So if you calculate the probability of this thing is going to be 95%. Okay. So how do we interpret the confidence interval? I think that's very straightforward, right? So in terms of interpretation of the confidence interval, I want you to remember the bounds are random variables. The bounds themselves, the bounds of the intervals are random. Beta j is not random. This is a one unique unobserved variable, unobserved number. But because beta hat j's are different numbers for every different sample that you're dealing with, this means that your lower bound and upper bound is going to be a random variable itself. So the confidence interval for different samples are going to be different. So let me actually, this is very interesting. So let's say if I work with one sample, if this is my beta hat j, let's say 0.85. Let's say I will get this confidence interval. Now if I work with another sample, let me use another color. In another sample, it was 0.9, so this will be my confidence interval. If I use another sample, you get the idea hopefully. Let's do blue, 0.08. This will be my confidence interval, right? So the confidence interval itself is going left and right, depending on what is the coefficient of the beta hat j that you're calculating, right? And it's going to shrink and expand depending on your significance level as well. So let me actually talk about it here too. So let's say this is my 0.085. If this is my 95% confidence interval, lower bound and upper bound, so what do you think the 90% confidence interval look like, or 80% confidence interval look like? Think about this one. So let's say this is my 95% confidence interval. So what do you think the 90% confidence interval look like? So let me draw. This is going to be my 90% confidence interval, right? If I want to go over 99%, so the range is going to be even wider. Because again, it's intuitive. You're expanding the probability, so you hope the upper bound and lower bound are going to expand as well. You can think of it differently as well. Look at the critical values. So the critical value for 1% significant level is going to be greater than 5% and greater than 10%, right? So it means that the lower bound is going to be smaller and smaller, and upper bound is going to be larger and larger. Okay, so that's one important thing. The other one is that in repeated samples, okay, if you do these things thousands of times, the interval will contain the population regression coefficient in 1 minus alpha % of the time. So what does this say? It says that if you do this sampling thousands of times, the way that we interpret confidence interval is that that interval that you calculated is going to contain your coefficient with, if alpha is 5, 95% probability. Okay, so there's a right interpretation and wrong interpretation. So the right one is this, that if you say the confidence interval will contain beta j with, let's say, 90% probability. This is a right way. What is a wrong way of saying that? And people use this wrong version of interpretation of confidence intervals a lot, but I want you to realize that that is wrong. So they say that beta j will lie in confidence interval with 90% probability. You might want to say that, wait a minute, these are the same thing. No, they're not the same thing. So let me tell you what's going on here. This is important. The confidence interval is a random variable, not the beta j. Beta j is not observable. You cannot say that beta j will lie in that confidence interval. However, you can say if that confidence interval is going to contain your beta j or not. Okay, it's a very subtle thing, but I think it doesn't hurt if I point it out, and I don't mind if you use them interchangeably because many people do that, but just be aware in terms of terminology. If you want to be accurate, you have to say with 95% probability, that interval will contain the population parameter beta. Okay, so here are just some rule of thumbs, I believe. So imagine if you're looking at the significance level of 1, this is a critical value for 1, then this is the probability is going to be 99%, 95%, 90%. Again, these are for different significance levels. There's nothing special here. Of course, if your significance level, let me do it this way. If your significance level is 5%, so what does it mean? 2.5% here, 2.5% here. So the interval in between, the odds are 95%, right? Again, nothing special here. Okay, now the important thing that I want you to remember is this one. What is the relationship between confidence interval and hypothesis test? So this is a very cool thing. So far, I told you that you can come up with a rejection rule in 2 different ways. First, compare the t-stats with the critical value. Second, compare the p-value with the significance level alpha. And now I'm introducing the third one. Third, see if that confidence interval contains your population parameter under the null. So this is a third way. And guys, all of these 3 different ways are telling you exactly the same story. So you shouldn't be surprised that now if one of them is rejecting the null, the other one must reject the null, the third way must reject the null, right? So you cannot, this is a wrong statement. It says that okay, the t-value approach reject the null, the p-value approach fail to reject. It's impossible. Mathematically, it's impossible. Okay, so let's see what is the relationship between confidence interval and the hypothesis test. We are going to say that if that interval contains our population parameter under the null, remember, this is my null. Beta j is equal to aj. This aj can be anything. 0, if it is 0, no, or 1, or 2, or whatever. The idea is that if that interval does not contain aj, then we reject the null. Means that hypothesis that you said beta j was equal to aj is wrong, was far from whatever you're discussing. So let me actually plot the distribution for you, and hopefully it makes more sense. Look at that. Imagine this is my beta j. I already told you guys that we can go ahead and construct a confidence interval around this beta j. And we say that with 95% probability, let's say this is the idea, with 95% probability, this interval, lower bound and upper bound, will contain beta j. Let's say I want to test if beta j is equal to 0, right? And again, let's imagine, I just want to show you a case that we reject the null. Imagine here is 0. Does everybody see that this interval does not contain 0? So in other terms, 0 does not belong to that interval, lower bound and upper bound. Does everyone see that? Okay, so this means that it is good news. We reject the idea that beta j was equal to 0. This is wrong, right? So in short, if that interval contains 0, bad news. So we fail to reject. If it doesn't contain 0 or aj in general, good news, we reject the null. And it is consistent, guys, remember, it is consistent with the t-value approach and the p-value approach. And okay, so let's see what else we have. Oh, one thing that I guess I forgot to mention is that confidence intervals, by definition, by constructions, are two-tailed. Right? We have one tail on the left, one tail on the right, lower bound and upper bound. Okay. All right, now let's look at some examples. And in this example, I want to go over the 3 different approaches and show it to you that no matter what approach you use, you will get exactly the same conclusion in terms of rejecting the null or not. And we're talking about the statistical significance. All right. So imagine we are regressing R&D. This is spending on the R&D. And because the spending is in dollars, it's widely distributed, we're going to use log. Okay. So we are regressing log R&D on log sales. Again, because sales is in dollars, it's widely distributed, we use log. And then this is profit as percentage of sales, well, profit margin. The profit is a percentage of sale, right? So Let's go over the intuition first. Imagine these are the numbers, the coefficients are positive. So intuitively, what does it mean? It means that so if the sale is increasing, then the amount of money you spend on R&D is going to be positive. It's going to increasing as well. This makes perfect sense, right? And we have the number. This is log-log model. So for sales, we say 1% increase in sales will lead to 1.08% increase in R&D spending. So far, so good. Okay. What about profit margin? And of course, if your profit margin is larger, it means that the company is doing better. So we can think of the positive relationship between R&D and profit margin, because you're going to spend more on research and development, and hopefully you're going to increase the profit margin even further. How we interpret this number? If profit margin increased by 1 unit, and the unit is percentage, so it means that if your profit margin increased by 100%, 1 unit, then the amount of spending that you have for the R&D is going to be 2.17%, log level model, right? Again, I hope that you get to a point that you can interpret these numbers very quickly, okay? And hopefully you will get there soon, no worries. Okay, so that was in terms of interpretation, right? So this is easily we interpret these numbers. Now, let's see, what can we say about the significance of the beta hat 1 and beta hat 2? Let me actually go ahead and do it. I don't know. Let's do it. Let's go only consider this one for beta hat 1. Okay. For beta hat 1, I'm going to use the t-stat approach. So the t-stat approach, beta hat 1. Okay. So let's go ahead and calculate the t-stat for beta hat 1. So what do I have? I have 1.084 minus 0. I'm gonna test if it is relevant or not. Divided by 0.06. Okay. And actually, let me pause the video and do the math and come back. Okay. So this number is around 18. It is huge. So I'm already super happy, because regardless of the significance level, if it is 1%, 5%, 10%, whatever, if I calculate the critical value for, let's say, 1% for a two-tail, I know that it's going to be around 2.4. I'm using those rule of thumbs because maybe this, this 18 is way larger than 2 point something, so I really don't care if it is a normal distributed or t-distribution. I use the approximation. So because t value is greater than 2.4, we're happy, reject the null. What was null? The null was that sales was irrelevant. So what can I conclude? I conclude that this variable sale that you have here is a statistically significant one, right? So it's statistically significant. For this one, so this was the first approach. The second approach, I have to calculate the corresponding value to that t-statistic, which was 18. And remember, this is 18 far on the right, this is minus 18 far on the left. If you calculate either of these shaded areas, you will see that it's going to be a very teeny tiny number. And actually, you have to use R. So for instance, for this one, what do? We do P, T, and minus 18. Degree of freedom is n minus 3, right? Because I have two exponential variables. So it's 32 minus 3, it's 29. So if I do this in R, let me actually go ahead and do that. I will get literally 0. The number was 1 point something. I think it was 3 multiplied 10 to the power of minus 16. It's literally 0. So it is not surprising. I knew that this area is very, very small because my t-stat is super large. If I multiply it by 2, really doesn't matter. So my p-value is literally very close to 0. This is awesome news. Small p-value, large t-stat. The same story. We like them both. We reject the null. We reject the idea that sale is irrelevant. So sale was relevant. Now the third approach. So for the third approach, let's construct the confidence intervals for them. So the confidence interval, remember, it's my beta hat 1, 1.084, multiply plus minus critical value for 5%. So let's say the critical value for 5% is 2.045. Multiply the standard error. I get this confidence interval. Look at the confidence interval. It's something between, let's say, 0.96 and 1.21. And imagine this is 0. You see, this interval does not contain 0. Good news. So I hope you get the idea. Regardless of the method that you use, you will get to the same conclusion. So here, the log sale was relevant because the confidence interval did not contain 0, or t-stat was greater than the critical value, or p-value was very, very small. They're all telling you the same story. So it turns out that in this example, log sale is relevant. It's statistically significant. Let's do exactly the same exercise for profit margin. And I'm going to do only work on the confidence interval. I highly encourage you to do exactly the same thing. Calculate the t-stat, calculate the p-value as an exercise for yourself. Okay, now if I go ahead and construct the confidence intervals, so what do I get? 0.0217 plus minus this critical value, multiply the standard error. What do I get? Look at that. This interval contains 0. 0 is in between. This is bad news. So I failed to reject the null. I failed to reject this idea that profit margin is irrelevant in terms of R&D spending. Okay. So let's read through this text because both of them are important. If the confidence interval does not contain 0, it means that the effect of sales on R&D is relatively precisely estimated as the interval is narrow. If I work with another sample, I'll get a number between 0.96 and 1.21. Whatever it is way greater than 0. Okay. Moreover, the effect is statistically significant, and it's different from 0 because 0 is outside of the interval. Okay. However, the effect of profit margin on R&D is imprecisely estimated, as the interval is very wide and it does contain 0. So it is not even statistically significant because 0 is between in that interval. And to be, again, the correct version of saying that interval contains 0. Okay. I think even the Wooldridge himself in the textbook used this, which is not accurate. So for that reason, I'm not going to be super picky, but I just want you to be aware that what is the right version of that statement. Okay, so we're almost done. The rest of it is just fun. We can quickly see how we can do it in R. So I'm not going to go over the R Studio. Let's do it here. So let's say, and I'll provide the R script on the Canvas page. So let's say we are calling the libraries Wooldridge Stargazer. I'm regressing R&D on sales and profit margin. So this is the one that we just explored. This is the data set. And look at the summary. So here's the summary. And as you can, do you remember we calculated this t-value for log sale? It was 18. Here we can look at the answer here. And do you remember it was 1 point something multiplied 10 to the power of minus 16. So here, this is the p-value. So p-value super small, t-value super large, very good. Log sale is super significant. What about the profit margin? T-value is small, p-value is large, is 10, and then this is bad news, it's not significant. Okay. All right. So what else I wanted to say? Look at this p-value. Let's interpret this p-value. What does it mean? Do you remember that the p-value was the smallest significance level that we can reject the null? So what does it mean? It means that if alpha is equal to 15%, good news, we rejected at 15% because p-value is less than alpha. So we reject. However, if alpha is 5%, we fail to reject. Why? Because p-value is larger than 5%. What is that 10.1%? It says that 10.1% is the significance level that I'm indifferent between rejecting and not rejecting. Hope now that you can get a sense of what is p-value and what do we mean by the smallest significance level that we can still reject the null. Okay, so that was the first part. Then let's find the critical value in the second part in R. So again, we're going to say that degree of freedom is number of observation n minus k minus 1. So what is k? 1, 2. So n minus 2 minus 1. Alpha is the one that we set. As a researcher, we can set it as 5%. You can go ahead and change this number in R, 10%, 1%. And look at that. This is a general version for calculating the p-value, the critical value, right? QT. We are looking at the quantile. QT of 1 minus alpha over 2. Remember, here's alpha over 2, here's alpha over 2. And what are the numbers? The number is 2.045. So if you're wondering where did we get this 2.045, here, this is how we do it in R. Now we can look at the t-stat itself. So I know that the summary MRM will give me this table. Out of that table, I can call, by using $, I can extract the coefficients. So these are the coefficients. And from those coefficients, these are, all of these things are the coefficient. From those coefficients, I can only look at the column, which is t-value. So if I run this line, so I get this. So these are the t-values, minus 9.3, 18, 1.6. So it seems the intercept is significant, log sale is significant, profit margin is not significant, but we do not necessarily care about the intercept, especially when I have only 2 exponential variables in the model. All right, and then finally, that confidence interval that seems to be daunting in terms of confusing, look at that, how we do it in R, cannot be easier. Just use conf_int function, you pass the regression, and in the level, we have to say 95%, 90%, whatever, because alpha is 5%, so this is going to be 95%. And these are the numbers. So these are the ones that we calculated. Now I want you to pay very good attention, going back to the fact that all these things should tell you the same story. If I use a t-value approach, reject the null, fail to reject. If I use the p-value approach, very, very small, reject the null, fail to reject at 5%, for example. If I use the critical value approach for 5%, reject the null because it does not contain 0. Do you see that? -5 to -3. Okay, reject. Reject the null because it does not contain 0. Fail to reject. Why? Because it does contain, this is at 5%. Well, it's very close to 0. This is profit margin. Yeah, I think at 5%, I need to take a look at this one. This number should be negative because we failed to reject at 5%. Something is going on. I'll double check this and talk about it in the class. Okay, so most probably something is missing. All right, but hopefully you get the idea of that. That interval should contain, because if you go back here, you see this interval was this. Minus something to plus something. I don't know what's going on here. Okay. Oh, my bad. You know what? It was negative. You know, I highlighted it. I forgot to. So this is negative number. So yes, it is correct. We failed to reach it. I just checked it out, and then so okay, I made a mistake here. This is negative. So negative, positive. So 0, of course, is between the two. Okay. So nothing wrong there. All right, so let's pause the video here, and in the last section, I'm going to talk about another type of hypothesis testing, which is a linear combination of parameters. So let's write it here. This is the 5th version. Testing. Well, let me use blue. Linear combination of beta j's. Okay, so see you in the next one.